this lecture, we are going to talk about stereoisomers and optical activity, but I actually want to start with an example of assigning absolute configuration to this molecule. It's trans 1-dimethyl-cyclopentane. So we have two chiral centers, the carbons with the methyls, so we can show the full tetrahedral of each by drawing the hydrogens that were not included, and then individually assign R or S to each center. Okay, so we'll do the center on the right first, this one here. So we have the lowest priority, the hydrogen gets the 4, then we have carbon of the CH3, carbon of a CH2, carbon of a CH2, okay? So we can make a decision there at those 3 carbons. We go 1 atom away. So if we go away this way, there's another CH2, or a carbon bonded to carbon, HH. If we go up this way, this carbon is bonded to carbon. Write little notes on here. So this carbon is bonded to the carbon that we started from. It's bonded to a second carbon, this one right here, and then H and H. Okay. Carbon here is bonded to the carbon that we started from, bonded to this carbon, and then H and H. Okay, so we can make a decision there. This carbon we can already rule on. It's bonded to the carbon that we started from, H, H, and H. So that carbon is going to get the second lowest priority, or 3. So, wait, 3? Yes. So we're trying to decide which carbon or which group gets 1, 2, 1, or 2. Okay. So as we're trying to figure out, we can make a decision here versus here. So we move 1 carbon away on that chain. Now we're going to compare this carbon, which is bonded to carbon, carbon, hydrogen, hydrogen, to this carbon here, which is bonded to carbon, 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 and hydrogen. So there's a difference, but there's a difference in this list versus this list. So this group, well, I don't want to try another color. This group is going to get the higher priority, which would be 1, because when we find the point of difference, we had carbon, 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 hydrogen versus carbon, carbon, hydrogen. And notice that I'm writing those in order of atomic weight to make this easier to compare this list to this list. So now we have our priorities. So, this might be obvious to some of you. I think I raised the wedge here, that going towards the carbon that you get to the methyl sooner will give you a higher priority. So if that's obvious to you, then you don't have to do these little lists. But if that's not obvious to you, and in some cases it might not be, you can make your list of priorities there. I'm going to just redraw this molecule. So here's your 4. So this was 1, 2, and this is 3. Okay. So the hydrogen is in the front here, and the fourth part is in the front. So we're backwards. Right. So if you were to go like this looks like S. But 4 is in the front. So it's actually R. Okay. You could redraw the molecule. So rotate this molecule. And then you're going to say, wasn't that just the same molecule? It's actually not. So this, call this one 1, 2, and 3. Now this would be 1. There's probably really no point on doing this. And then this would be 3. But anyway. Okay. So yes, it does look the same, but it is not. This is a chiral molecule. You don't have a mirror here. Okay. You don't have a mirror there. So now 4 is still 1, 2, and 3. So now you can see with the hydrogen in the back that this is in fact R. So if you already answered it and you got to R, make sure that you did have the 4 in the back, or that you considered it as being in the back. So you're not just getting the wrong answer. And note that this is no mirror, no mirror. Okay. So this is RR, so both of these centers are R. So this one is R, and this one is R. Okay, so we come back here, RR. Okay, lots of information there. I'm gonna go ahead and move on. So we're gonna talk about the differences in enantiomers. And so here I have a table of 2 enantiomers in R and an S. So all the chiral centers in a pair of enantiomers have to have opposite absolute configuration. There's only one chiral center in these 2 molecules, but if there were 2 chiral centers and one enantiomer is RR, the other one has to be SS. So that's what we mean by all chiral centers have to be inverted. Now I'll show you more examples. All the physical properties of enantiomers are the same boiling point, same melting point. So we cannot separate enantiomers by their boiling point. By distillation, we cannot separate them by crystallization because they have the same melting point. They have the same refractive index, they have the same density. They do differ, however, in their optical activity, which is the ability of any chiral molecule to rotate plane polarized light. So not just molecules that have enantiomers, but any chiral molecule can rotate plane polarized light. So what does that mean? So light moves through space as waves. Visible light, those waves have wavelengths between 400 and 700 nanometer. So here we have light from a sodium lamp. Which has a wavelength of 589 point, oh, not yet, of a sodium lamp, pass through a filter, a polarizing filter. So a polarizing filter is like your polarized sunglasses. It takes all the waves and all of light and filters them to only let some wavelengths pass. So here's where I meant to write that 589.6 nanometers. Okay. Now, if we pass that filtered light through a sample containing a solution or a pure liquid containing chiral molecules, one type of chiral molecule only, so it could be like an R enantiomer, that molecule will rotate the light, will literally change the degree of the light. If it rotates the light clockwise, we say the molecule is dextrorotatory and assign it a plus, counterclockwise, laboratory, and assign it a minus. So enantiomers differ in the direction in which they rotate the light, but not in the magnitude. Okay, so I don't have the numbers for these specific enantiomers, but this could be plus or minus in optical activity. And then its enantiomer has to be the opposite of whatever that may be. So we can't predict if an R enantiomer is going to be plus dextrorotatory or minus laboratory, there is no connection between R and S and plus and minus. We just have to measure it. Okay, so don't assume R is plus, R could be minus. And there are some examples later on in this slide or in the slides. Okay, we can have, oh, here's an example. Okay, we can have a mixture of enantiomers that's a 50-50 mixture, 50% one, 50% the other. So here's this compound S plus butanol or 2-butanol. So it's S based on our Conigal-Prelog rules. You know, here's 1, 4, 2, 3. So there it's S. Okay, so convince yourselves of that. And then it's plus, meaning that it rotates plane polarized light in a dextrorotatory. That's an example of S being plus, right? So it doesn't have to be minus. It's an enantiomer, we don't even have to check it. If it's S plus, it has to be R minus, right? If enantiomer A is S plus, enantiomer B has to be R minus. Same degree of rotation, just different direction. Okay, so if you have a 50-50 mixture of these two enantiomers, we call it a racemic mixture. And then if we show plane polarized light through it and try to rotate the degree of rotation, it would be 0. Okay, so there is no optical activity in a racemic mixture, a 50-50 mixture, because they cancel out. And that mixture might have a different boiling point, different physical properties from the pure enantiomers. So we can refer to the optical purity of a mixture. A lot of times in organic chemistry, reactions produce a racemic mixture. And in some cases, it might not be a racemic mixture. It might be like 70-30. And then we have an excess of one enantiomer, and we call that enantiomeric excess. So we won't show here how to calculate the enantiomeric excess. People spend a lot of time trying to push the enantiomeric excess to 100% to get a molecule that's pure. You know, you might have to do these calculations in the future, but here I'm just interested in the vocabulary. What does it mean to be optically pure? And what does it mean to have an enantiomeric excess? And of course, what does it mean to be a racemic mixture, which nothing is an excess, 50-50. Okay, so enantiomers were first discovered by Louis Pasteur. He had crystallized the molecule sodium ammonium tartrate that has 2 chiral centers or 2 chiral carbons. Here's one, here's the other. Here is wine crystals. So wine crystals are tartrate, a potassium tartrate in this case. And what you see is that the crystals are really large. So because these crystals that Louis Pasteur grew were so large, he could see them with the help of a microscope. And actually, I mean, you could see them with your naked eye, but to separate the crystals, he used a microscope. Then what we see is that all of the R enantiomers crystallized together, all of the S enantiomers crystallized together, and he was able to physically separate them and make one pile of each, and then showed that they polarize, or that they rotate, excuse me, plane polarized light in opposite directions, right? Which is, of course, the only way that enantiomers differ, and the direction in which they rotate plane polarized light. How might we use this? Well, this is kind of a fun example. Many drugs, many natural compounds are chiral molecules. Cocaine is an example of this. Okay. Oh, you know what? I think there's a slide missing. Oh, okay. Now my slides are in reverse there. So here is the symbol for specific rotation. So the specific rotation of penicillin 5 is plus 233. This was measured using a sodium D line, which is just saying that specific 589.6 nanometer lamp. So that's what the D refers to. So the specific rotation is the degree observed and with the directions of plus or minus degree divided by the concentration of the sample that we're measuring. Okay, and the concentration, it's actually given, in grams per cubic centimeters. Okay. The length of the cell that we're using in decimeters. Okay. And then the degrees is just degrees. So plus or minus, whatever that may be. Okay, so we can look up tables of this. Sucrose is a chiral molecule, so it has a specific rotation, CAN4 also, but chloroform is achiral. So it doesn't have a specific rotation. So here we have chiral, 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 cholesterol is chiral, morphine, cocaine, but acetic acid is achiral. Okay, so this is assuming pure enantiomers of each one of these compounds when recording that specific rotation. Now we could also solve for the observed rotation, which would just be the specific rotation. So the brackets mean specific rotation times the concentration times the path length. Okay, so actually let me go back to the picture and show you what I mean by path length. So path length would literally mean this distance here. Okay, and that sample cell is holding the solution of that specific concentration C that we're referring to. So the amount of molecules in the way of the light matters. Okay, so all I've done is just rearrange this equation. Now let's go back to that example, the cocaine example. So a police officer confiscating 1.20 gram sample of what they suspect is cocaine, which is a chiral molecule. A laboratory technician dissolves the sample in 7.50 mils of chloroform, which is achiral, so it doesn't interfere, and placates it, meaning they put it in the sample cell that's 5.00 centimeters path length. If the sample is indeed cocaine, what will be the observed rotation? Whoops. What will be the observed rotation when the sample is put through a polarimeter? So I don't know if I've said that word yet. Polarimeter is the name of the instrument that we use. Now here's the specific rotation of cocaine. So we already know specific rotation times concentration, right, times the path length is going to give us an observed rotation. So you might write observed there just to remind yourself what that means. And that's what we want to know. We want to know if this is in fact cocaine. We can look up this number for cocaine. We can measure the concentration from the information given, the path length. What would we expect that observed rotation to be? So we have negative 16 degrees. The concentration here, it's, remember, in grams per cubic centimeters. A milliliter and a cubic centimeter are the same magnitude. So 1 milliliter equals 1 cubic centimeters. Okay. Let's see. You know, I think I lied to you because the specific rotation is degrees times the inverse of concentration over decimeters times gram. There we go. So the concentration for the specific sample that they use here, we have, where's grams? Right here. We've done a different number. I know. 1.20 grams of sample, okay, divided by 7.50 cubic centimeters. which is the same as just 7.50 milliliters. 5 centimeters is the same as 0.5 decimeters. 0.5. Keep the right number significant figures there, decimeters. Okay, so centi meaning 100, deci meaning 10, that's the prefix. So I just divided by 10 to get to decimeters. Okay, so how I realized that I lied to you about the units is because they need to cancel out. Grams cancel out with grams, decimeters with decimeters, cubic centimeters with cubic centimeters. So we expect to see a rotation of negative 1.3 degrees. If the sample is in fact cocaine, which would have this optical rotation. All right. Let me go forward. Go ahead and correct. Did I write it anywhere? Oh no, I didn't. I didn't write it anywhere. So I didn't lie. I just lied to myself. Okay. So now to take the point here, these are chiral molecules. Okay, chiral molecules. They don't have to have an enantiomer. They just have to be chiral, and we can look up these tables pretty easily. Okay, so what about stereoisomers with multiple stereocenters? Well, we have already seen our enantiomers, okay? And we looked at some examples with multiple chiral centers. If we have n chiral centers, the maximum number of stereoisomers is 2 to the n. Right, so if we have n equals 2, that's how many chiral centers, and we have 2 to the 2, or 4 stereoisomers. Possible. And I say possible because there are some cases in which symmetry gives us a meso compound, and meso compounds don't have an enantiomer, and that takes away one or more stereoisomers. Okay, so we'll see an example of meso compounds. So stereoisomers that are not mirror images, but are still stereoisomers by having the same connectivity, are called diastereomers. Okay, and they don't all have the same or the inverted chiral centers. So let's look at an example. So draw the stereoisomers of 2,3-pentane diol and determine their relationship to each other. So I'm going to erase this just to have some room. All right. So I've given you here the line bond structure without showing any stereochemistry, meaning we don't have wedges and dashes. So I'm going to make my life easier and make this a wedge so that I can put the hydrogen, the lowest priority, in the back, right from the get-go. Okay, and then I can assign RS to this. So here's 1, 2, 3, and 4. So this is R. 1, here's still 2, 3, and 4. So this one is S. Okay, so this is the RS stereoisomer. That's one of them. So I have 2 chiral center here. So the maximum I can have is 4 stereoisomers. So now I'm going to draw the enantiomer of this molecule that I drew, which has to have SR configuration because it has to be all inverted. To do that, I'm going to keep the orientation the same and just invert the centers. So the hydroxides were coming forward, the wedge, now they're going back. Okay, that's the enantiomer. You can prove to yourself that that is an enantiomer. 1, 2, 3, 4. It looks like R, right? It looks like R, but the but the 4 is in the front, so it's actually S. So now if I come back to the original stereoisomer and I keep 1 carbon the same, so not inverted, so I'm going to make it a wedge. and invert the other one. So this one I'm going to invert and make it a dash, the hydroxide. I have an R stereoisomer rather than an RS or an SR. So you can prove that to yourself, RR. So now how are these related? Well, they are not superimposable and they are not mirror images, but they're still stereoisomers because they still have the same connectivity, right? They still have the same formula, same connectivity. So they are diastereomers. So a molecule may have many diastereomers, but only one enantiomer. Okay, a molecule may have many diastereomers, but only one enantiomer. A molecule may have many diastereomers, but only one enantiomer. So we're still missing the SS, which is the enantiomer of RR, and the diastereomer of the other two molecules that I have written on the board. So if I invert this hydroxide, so now I'm inverting RR. Oh, invert OH. Okay, so these are enantiomers. Okay, and that's SS. You can prove that to yourself if you need to. Now, if I compare this SS to my original, those are diastereomers of each other. If I compare, because they're not completely inverted, my RS is not SR down here, right? It wasn't inverted to SR, so they are not enantiomers, they are diastereomers. Okay, and then these are diastereomers of each other. So if you look at any one of these stereoisomers, it has one enantiomer and then two diastereomers. Okay, and there are no more stereoisomers for 2,3-pentanediol. So if we wanted to write the name more complete with the absolute configuration, write 2R, 3R, pentanediol. And I try to be very specific and say include absolute configuration. So you have to know what that means, RS, RS. And then of course you can put S, 2S, 3R, 2S, 3S, and then 2S. I don't know which one I haven't said. Okay, but you get the point. Okay, so here's just the same thing summarized, although perhaps not in the same order. So when do we lose some of the stereoisomers in our maximum? When we have meso compounds, which are achiral because they have a symmetry plane, a plane of symmetry, but they are still containing asymmetric centers. Okay, so here's a compound. If I gave you the Lyman structure, it would look something like this. 1, 2, 3, 4. And then OH, OH. So you can make this a wedge and this a wedge to get one stereoisomer. Okay. You could draw its enantiomer, which is inverting every center. And then you can try to draw two diastereomers. So invert the first hydroxide, but leave the second one a wedge, or retain the first hydroxide and then invert the bottom one. Okay. What you might see is that these two are actually the same, but you might need to redraw it. Okay, so if I redraw this, I can rotate it, and then I would end up with the molecule on the right. Okay, if you think about rotating it, because the hydroxide that's on the dash would now be up here, and it would still be on a dash if I rotate just 80 degrees this way. Now, if I redraw this by rotating not 180 degrees, but just rotating about the bond, like this. So keeping the wedge here, and then bringing the hydroxide that's on a dash up. So in that case, it will be a wedge. I can see the mirror plane right there. So molecules that have an internal plane of symmetry are achiral. And the pictures up here are doing the same thing. They're achiral. And the bottom is how you would go about doing this analysis. But these are still asymmetric centers. And they're still asymmetric centers. The really cool thing about meso compounds is that the asymmetric centers actually mirror each other. And therefore they have opposite absolute configuration. Okay, so here's your, so this one, 1, 4, 2, and 3. So there's your S. So I don't even have to check, this one has to be R. So let's check. 1, 2, 3, and 4. So they mirror each other. So when we have a meso compound with 2 chiral centers, we only have 3 stereoisomers because what looks like a pair of enantiomers is actually the same molecule. So if we had 6 stereoisomers, we might only have 4 total because 2 are the same. Well, no, you have to kind of check the planes of symmetry to see, well, as the number increases, what's the symmetry doing? As the number of stereocenters increases, I mean, what's the symmetry doing? Is this symmetrical or is this not symmetrical? Because if the molecules are symmetrical, then we might have meso compounds. Okay, so now that we know about other stereoisomers, let's refresh our memories on the property. So enantiomers only differ in their specific rotation direction, to be more specific. And so we can't separate them. We can separate diastereomers because, well, most of the time, because they have different physical properties. So we have seen geometrical isomers already with rings, but here's an example with alkenes, in which we have cis versus trans, meaning that the groups are on the same face of the double bond or on opposite faces. These 2 molecules can be easily separated. They have, well, maybe not easily, their boiling points are pretty close, but they have different polarities. And we can see that if we show the dipoles. So you might not realize that this is a polar bond because it's carbon bonded to carbon, but an sp2 carbon might actually be more electronegative. And that's what we observe. An sp2 carbon tends to be more electronegative than an sp3 carbon. So that is a polar bond there, and this is a polar bond as well. So those dipoles of the bonds cancel out, gives us no dipole moment for the molecule, but here they don't cancel out. Everything's working in the same direction, so there is a dipole. So there's just a little piece of information we have not seen yet, that depending on the hybridization of the atoms, the electronegativity doesn't have to be the same. On the right is an example of sugars. We'll learn this Newman projection next class. Here you have a plus and then a minus. So I'm not sure which one's plus, which is minus, I think. This one's plus and this one's minus. Well, anyway, so these are enantiomers of each other, right? Enantiomers. Because it doesn't really specify which is plus and which is minus, but that doesn't matter. Here is a diastereomer of those 2 enantiomers. It's a meso compound, and we can't separate the plus and minus from each other of the dibromosuccinic acid, but the meso compound, we could separate it from the mixture here because the melting points are significantly different, so we could crystallize them. So diastereomers do differ in their physical properties. We see dipole moment on the left, and then we see melting points there on the right. But enantiomers have the same physical properties. And then we have to remember that we have those racemic mixtures of enantiomers, and we have mixtures of enantiomers that are impure. So you might have one enantiomer more than the other, and then it's no longer racemic. So the properties will change based on the mixture percentages. So how could we separate enantiomers if we needed to? Well, Pasteur showed us how to do that. You could crystallize them separately. So you have a chiral molecule, and then an achiral base here. You still have enantiomers. Crystallize them, pick them apart. This is known as fractional crystallization. It is uncommon because you do need to have fairly large crystals to be able to pick them out under a microscope. A more common way is to take our enantiomers, so here are enantiomers, and then turn them into diastereomers, which will have different properties. So if we have an RS mixture, a racemic mixture, it actually doesn't have to be racemic, it could be any mixture percentage. We could treat it with a chiral molecule. So in this case, we have an acid-base reaction. So acid, what's this acid right there? So now we have these diastereomers, the RR salt, the SR salt. They can be separated if they have different enough melting points. Okay, and then we could add acid back to get our acid enantiomers, but pure. So this is resolution. Taking enantiomers, turning them into diastereomers by reacting with a chiral molecule. Okay, it doesn't have to be a chiral base. Here, the example is an acid-base reaction. The point is taking enantiomers plus chiral molecule to get diastereomers, and then separating the diastereomers. So enantiomers mixture plus chiral molecule. I'm pointing at the board. Enantiomers plus chiral molecule to get diastereomers, and then we can separate the diastereomers. That's resolution of enantiomers. Okay, here's an overview. We know our isomers have the same formula. If they have different connectivity, we call them constitutional isomers. If they have the same connectivity, we call them stereoisomers. Well, assuming they have different spatial arrangement, because if they have the same spatial arrangement, they're just the same molecule. So within stereoisomers, we've seen our enantiomers, non-superimposable mirror images, like our hands. Oh, this isn't correct. You can have more than one chiral center. All chiral centers are inverted. So all centers inverted. All right. So if we had, for example, an RSR molecule, its enantiomer would be SRS. Okay. Diastereomers have to have multiple chiral centers. Okay, but enantiomers can have one, or they can have infinity. Diastereomers have to have at least two. Okay, they're not superimposable, non-mirror images, but because they still have the same connectivity, they're still stereoisomers. So for example, if we had an RSR stereoisomer, a diastereomer of it would be like RSS, for example. Okay, and there are many more, right? As long as not every chiral center is inverted, it's a diastereomer. So cis and trans stereoisomers fall within that category, and we'll come back to those in the next slide. We've seen our meso compounds, which are those diastereomers that contain asymmetric carbons or asymmetric centers, but still have an internal mirror plane, right? So the example I showed, there's internal mirror plane. The but we still have asymmetric carbons. So that's technically why we don't call these carbons chiral carbons, because this molecule is achiral. Okay, so let me come back to those cis and trans diastereomers one last time, just to show you how they are related. So one thing to point out, you cannot have an equilibrium between a cis and a trans diastereomer. And actually, let me put that aside for a second. Let me just show you what I'm mentioning. So here you have R. Okay, we assigned that at the beginning of the lecture. It's an enantiomer. Okay. Let's pretend you have a mirror right here. Here's your mirror. There's a mirror. There's a mirror, right? So it's mirrored right in. Right, so there's the mirror. It is SS. So that absolute configuration can help you prove to yourself that these are not the same molecule. These are, in fact, enantiomers of each other. Okay, it's because we lack that plane of symmetry. Now, both of these molecules are trans. Right? Both of these enantiomers are trans. We can look at the cis, and see there is a plane of symmetry here. So this is meso. Meso compounds are achiral, but they have asymmetric centers. So here's your R, here's your S. You might think, oh, let me put a plane of symmetry here, or a mirror plane there, or mirror, whatever. There's the enantiomer. No, it's not. That's actually the same molecule. A molecule, not an enantiomer. Right? Because you might say, well, this is S and this is R, but if you just rotate the molecule, they are superimposable. Right? You rotate. Okay, so these are cis, or this one molecule is cis. How are the cis and the trans related? Well, they are diastereomers of each other. All right, here you have the RR stereoisomer, here's the SS, and then here's the RS. Okay. So if we don't invert everything, like we do when we go from RR to RS, then we have diastereomers. Okay, so what I was getting at the beginning, you cannot invert a trans isomer to a cis isomer by something like a ring flip. Okay, so let's think about chair cyclohexanes for a second. We consider them separately. So I'm not saying there's like an equilibrium here. I'm just saying when you compare cis isomers to trans isomers, they are diastereomers. And when you compare trans to trans, they are enantiomers. Cis to cis, there can be enantiomers, just not in this example. Okay, so you know, like if we had something else here, you lose that plane of symmetry. I just like to use that example. Okay, so it's not always that this is going to be meso. That was just this specific example. Okay, when we look at cyclohexane, we might want to look at the chairs, but we don't have to. If we draw the line bond structure, which is here on the right, we can see for this cis dibromocyclohexane that there is a plane of symmetry right there. This is achiral, and this is meso. Right, so you can assign 4, 1, 2, 3, etc. as your R, etc., etc. You can assign absolute configuration. But if you jump over here to the chair, okay, they are non-superimposable, but the interconversion is fast. That makes them so non-superimposable, meaning they are enantiomers of each other. Okay, these are enantiomers. But the chair ring flip enantiomers are so fast that any sample that we have is going to be racemic. It's going to be optically inactive. So what that boils down to is we don't have to look at the chairs. We can just look at the Lyman structure, okay? Because even though the chairs might look like they are chiral, the equilibrium makes the mixture optically inactive, okay? Now, one thing the book glosses over, this is not how you're supposed to draw a ring flip. You know how you're supposed to write a ring flip? You're supposed to draw it by bringing the carbon that's up on the chair down, the one that's down up, and then moving a little bit clockwise. So here's your down equatorial. It's going to be down axial. I'm going to run into the writing there. And then here is your down axial. It's going to be down equatorial. And then you have to